The actual count, 60. 60 galaxies scattered across a region that should hold 2,000. The void is 97% emptier than it should be. Its density is about 3% of the cosmic average. In some regions deep within the void, the density drops even lower. Let's put this in perspective. Imagine a major city, say New York or Los Angeles. Now imagine that instead of 8 million people, only 240,000 remain. The highways still exist, the buildings still stand, but 9 out of every 10 people have vanished. The city feels abandoned, hollow, wrong. That's what the Boötes Void looks like to astronomers studying galactic distribution. Where did the missing galaxies go? The question assumes they were there in the first place. The evidence suggests they never formed. Something about this region prevented normal galaxy formation from occurring. However, the details of that process remain fuzzy. The 60 galaxies that do exist inside the void are strange in their own right. They're mostly dwarf galaxies, small and faint. They contain far fewer stars than typical galaxies. Many of them appear irregular in shape, lacking the elegant spiral arms or smooth elliptical forms seen in galaxies living in denser regions. These void galaxies evolved in profound isolation. Without nearby neighbors, they never experience the collisions and mergers that shape most galaxies. They never felt the gravitational harassment of passing through dense clusters. They simply drifted alone through the darkness, slowly converting their gas into stars over billions of years. Some of these galaxies are rich in neutral hydrogen gas. This makes sense. In isolation, with no external forces stripping away their gas reserves, they retained the raw material for star formation. However, they formed stars slowly, at a leisurely pace that reflects their quiet environment. The void galaxies sometimes align in a tube-like structure, running through the middle of the void. This pattern suggests the void might have formed from the merger of smaller voids, like soap bubbles, combining to create one large bubble. The galaxies mark the boundaries where smaller voids once met. Observing these 60 galaxies presents a challenge. They're faint. They're far away. Even with powerful telescopes, most appear as barely visible smudges of light. Amateur astronomers with large backyard telescopes can spot a few of the brightest ones, but they need excellent conditions and patience. The brightest void galaxy, designated Markarian 848, shines at magnitude 14.8. That's about 4,000 times fainter than the faintest stars visible to the naked eye. It requires at least a 10-inch telescope and dark skies to see. The mathematical mismatch between prediction and reality is what keeps cosmologists awake at night. 2,000 versus 60. The numbers don't just suggest something unusual happened here. They scream it. Something carved this hole in space and left it nearly empty. The Great Nothing. Names carry power. When scientists discover something that unsettles them, the names they choose often reveal their discomfort. They called it the Great Nothing. The name emerged informally among the research team shortly after the discovery. Before it became the Boötes Void in scientific literature, before it received its formal designation, astronomers working on the project referred to it simply as the Great Nothing. The name captures a visceral truth. This region feels like an absence, a hole punched through the fabric of the cosmos. Other cosmic voids exist. Astronomers have cataloged hundreds of them since the 1980s. They range in size from 20 million light-years across to several hundred million. Each one is a region of unusually low galaxy density, a bubble in the cosmic foam. However, the Boötes Void was the first one discovered, and it remains among the largest. The Great Nothing nickname stuck because it resonated emotionally. Scientists usually prefer technical, neutral language. They describe objects with coordinates, measurements, spectral classifications. Emotion rarely enters their terminology. However, this void demanded something more. When you spend your career studying galaxies, discovering their beauty, their complexity, their endless variety, encountering a region where they simply don't exist feels wrong. It feels like an error in creation, a place where the universe forgot to finish its work. The void sits in the direction of the constellation Boötes, the herdsman. In mythology, Boötes eternally pushes the Big Dipper around the North Celestial Pole. The constellation contains the bright star Arcturus, one of the brightest in the night sky. Ironically, this bright foreground hides one of the darkest regions in the cosmos behind it. When you look at that patch of sky, you see stars belonging to our own Milky Way galaxy. They're close, relatively speaking, just hundreds or thousands of light years away. Behind them, scattered through the near side of the void and along its edges, you might spot a few dozen faint galaxies with powerful telescopes. But beyond those, nothing. Just darkness. Just the great nothing. Some images circulating online incorrectly show the Boötes Void as a pitch-black, circular region completely devoid of any light. These images usually show Barnard 68, a dark nebula much closer to Earth. Barnard 68 is a cloud of dust and gas so dense it blocks light from stars behind it. It looks like a hole punched in the starry background. The Boötes Void is not like that. It's not a physical object blocking light. It's an actual void, a three-dimensional region where galaxies simply don't exist in the numbers they should. You can't photograph it in the same way you photograph a nebula. It reveals itself only through careful mapping of galaxy positions and distances. This distinction matters. A dark nebula is nearby and small. The Boötes Void is distant and incomprehensibly vast. One is a cloud. The other is an architectural feature of the universe itself. The emotional weight of the Great Nothing name reflects something deeper. It touches on a primal fear, the fear of cosmic loneliness, the fear of emptiness, the fear that the universe might contain vast regions where nothing happens, where nothing can happen, where isolation is absolute. If you could somehow transport yourself to the center of the Boötes Void and look around, you would see a handful of faint, distant galaxies scattered around the horizon. They would appear as tiny smudges of light, impossibly far away. The rest would be darkness, pure, absolute darkness in every direction. The Great Nothing perfectly describes what waits there. However, as we'll discover, this nothing is not quite as empty as it appears. The shattered principle. For decades, cosmologists operated under a comfortable assumption. They believed the universe was more or less smooth at large scales. Sure, you get stars clumping into galaxies. Galaxies gather into clusters. Clusters might even form superclusters. But if you zoomed out far enough, averaged over large enough distances, the universe should look uniform in every direction. This assumption had a name, the cosmological principle. It stated that the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in all directions. Blend the universe up like a smoothie and you get a uniform cosmic soup. The discovery of cosmic voids shattered this comfortable illusion. The universe is not smooth. It's lumpy. Wildly, dramatically, spectacularly lumpy. The lumpiness operates at scales far larger than anyone predicted. The Boötes Void and other supervoids revealed that the cosmos has structure on scales of hundreds of millions of light years. The cosmological principle doesn't collapse entirely. It still holds at the very largest scales when you average over billions of light years. However, at intermediate scales, the scales where we actually observe and measure the universe, the lumpiness matters. It matters a lot. The problem started innocently enough. In the 1970s, astronomers developed new techniques for measuring galaxy redshifts quickly. Before this, determining a single galaxy's redshift could take hours at the telescope. New instruments and methods let astronomers survey hundreds, then thousands of galaxies. These surveys produced three-dimensional maps of the universe for the first time. Astronomers could see not just where galaxies appeared on the sky's two-dimensional dome, but how far away they sat. The maps revealed depth. They revealed structure. What they found was shocking. Galaxies were not scattered randomly through space. They organized themselves into an enormous pattern. Long filaments of galaxies stretched across hundreds of millions of light years. Flat sheets or walls of galaxies separated vast, empty regions. At the intersections of walls, galaxies piled up in dense clusters. Between all these structures, voids. Massive, yawning voids. The pattern resembled soap foam or the structure of a sponge. Imagine a kitchen sponge with its network of solid material surrounding empty bubbles. The universe looks similar. The galaxies trace out the solid parts. The voids fill the bubbles. This discovery required rethinking fundamental cosmology. The equations describing the universe's evolution, developed by Alexander Friedmann in the 1920s, assumed uniformity. They treated the cosmos as a smooth fluid, expanding equally in all directions. These equations worked beautifully for describing the universe's average behavior. However, they completely failed to capture the local reality. The local reality is lumpy. The lumpiness has consequences. Gravity behaves differently in voids versus filaments. Time flows differently. Space expands at different rates. These differences are small but measurable. Accumulated over billions of years across billions of light years, they become significant. Some cosmologists began suggesting that the universe's apparent acceleration might actually be a side effect of this lumpiness. What if we're not properly accounting for how structure affects our measurements? What if dark energy is just an artifact of using oversimplified equations? This debate continues today. However, one thing is certain. The discovery of cosmic voids forced astronomers to confront an uncomfortable truth. The universe they thought they understood was far more complex than their models suggested. The smooth cosmic soup was a myth. Reality is messier, stranger, and far more interesting. But where did this structure come from? The cosmic web. The largest pattern in nature is invisible to the naked eye. You need telescopes. You need computers. You need millions of galaxy measurements processed through sophisticated algorithms. When you finally see it, the pattern takes your breath away. Scientists call it the cosmic web. Imagine a spider's web stretching across cosmic distances. But instead of silk threads, the strands are made of galaxies. Instead of empty air between the threads, you find voids. This structure fills the entire observable universe. It's everywhere. It's everything. The web has four main components. First, the voids. These are the bubbles, the empty regions where almost no galaxies exist. They range from 20 million to hundreds of millions of light years across. They occupy most of the universe's volume. 80% of space consists of voids. Second, the walls. These are sheet-like structures where galaxies cluster in two-dimensional surfaces. Imagine a soap bubble's surface. The walls of the cosmic web resemble these surfaces, except they're made of galaxies instead of soap molecules. The walls contain the typical cosmic density of matter. They're neither particularly empty nor particularly dense. Third, the filaments. These are the one-dimensional structures where walls intersect. Picture the edges where two soap bubbles meet. Filaments stretch for tens or hundreds of millions of light years. They contain higher concentrations of galaxies than the walls. Matter drains along filaments like water flowing through pipes. Fourth, the clusters. These are the nodes, the points where multiple filaments intersect. Clusters represent the densest regions of the universe. Thousands of galaxies packed together, bound by their mutual gravity. Clusters form at the junctions where walls and filaments meet, like knots in a net. This hierarchy exists because of gravity. Matter flows from low-density regions toward high-density regions. The voids empty out as their sparse matter gets pulled toward the denser areas. The walls collect this matter. The walls then drain along filaments. The filaments feed into clusters. The process happens slowly over billions of years. However, it happens relentlessly. The voids grow emptier. The filaments grow denser. The clusters grow more massive. The cosmic web evolves, with matter constantly redistributing itself. Our own galaxy, the Milky Way, sits on a filament. We're not in a void, thankfully. We're also not in a major cluster. We occupy a relatively average position in an average filament. Our location gives us a decent view of the cosmic web around us. We can see nearby voids. We can trace filaments stretching into the distance. We can observe clusters both near and far. The cosmic web's geometry determines the future of galaxies. Galaxies and voids evolve differently from galaxies and clusters. Void galaxies live in peace, undisturbed by neighbors. Cluster galaxies experience constant harassment, colliding and merging and having their gas stripped away by hot intergalactic plasma. The web also determines the distribution of matter and energy in the universe. Voids contain little ordinary matter, but dominate in volume. Clusters contain concentrated matter, but occupy tiny volumes. The walls and filaments hold the majority of ordinary matter, spread across intermediate volumes. Computer simulations can recreate the cosmic web's formation. Start with a nearly uniform distribution of matter, shortly after the Big Bang. Add tiny quantum fluctuations that create small density variations. Let gravity work for 13.8 billion years. The result looks remarkably like what we observe: walls, filaments, clusters, and voids. The cosmic web is not random. It's the inevitable result of gravity acting on an expanding universe with slight initial imperfections. It's beautiful, it's intricate, and it's all connected. However, what's most striking is what dominates the web. By volume, most of the universe is nothing. This statement sounds paradoxical. How can nothing be most of anything? However, when we measure the universe's volume and calculate how that volume divides between dense regions and empty regions, the math is clear. Voids occupy approximately 80% of the cosmos. 80%. Let that sink in. 4/5 of all space contains almost no matter, no stars, no planets, no gas clouds. Just vast, dark emptiness, separated by thin walls and threads of galaxies. This ratio has profound implications. We live in the minority of the universe. Our galaxy exists in a dense region, relatively speaking. We're on a filament surrounded by other filaments and walls. From our perspective, the universe looks crowded with galaxies. We can see thousands of them with large telescopes, billions with the most powerful instruments. However, our view is biased. We see the bright structures because that's where we live. We're like a fish in the ocean who assumes the entire world is water. The fish never experiences dry land, never sees the atmosphere, never knows that most of Earth's surface is not ocean. Similarly, we experience the cosmic web's dense parts. The voids remain mostly hidden, visible only through careful mapping and statistical analysis. If you could randomly place yourself anywhere in the universe, you would have an 80% chance of appearing in a void. You would look around and see almost nothing, a handful of faint, distant galaxies scattered across the sky. Everything else would be darkness. This probability reveals something important about cosmic structure. The universe is defined more by its absences than its presences. The places where galaxies don't exist occupy more space than the places where they do. Think about that from an information perspective. If you wanted to describe the universe's structure, you could list every galaxy's position. However, it might be more efficient to list every void's position and size. There are fewer voids than galaxies, but they take up more space. The voids are the primary structures. The galaxies just outline them. The 80% figure also matters for understanding the universe's evolution. Voids are not static. They grow as the universe expands. Voids expand faster than the average expansion rate. This happens because voids contain less matter, which means less gravity holding things together. With less gravitational resistance, the expansion proceeds more rapidly. Meanwhile, dense regions expand slower than average. Gravity in clusters and filaments partially counteracts the cosmic expansion. Clusters might not expand at all internally. Their gravity is strong enough to hold them together against the expansion. This differential expansion means the 80% figure is increasing. Voids occupy a larger fraction of the universe's volume today than they did 1 billion years ago. 1 billion years from now, they will occupy an even larger fraction. The universe is becoming more empty with time. Currently, if you could swim through the deepest parts of voids, you might encounter a single hydrogen atom in a space the size of a football field. That's the density. One atom per several thousand cubic feet. In denser parts of voids, you might find a few more atoms. In the absolute deepest regions, even that sparse matter vanishes. For comparison, the interstellar space between stars in our galaxy contains about 1 atom per cubic inch. That's already a vacuum far better than anything we can create in laboratories on Earth. The voids are 1,000,000 times emptier than that. Some regions within voids are so empty that even dark matter thins out to near nothingness. These are the lowest density regions in the entire universe. Nothing approaches their emptiness. Yet, despite being 80% of space, voids remained largely ignored by astronomers until recently. Scientists focused on galaxies and clusters where the action happens, where stars form and die, where black holes devour matter and release energy. The void seemed boring, just empty space, nothing to see, nothing to study. That assessment was wrong. The first whispers. The story of cosmic voids begins at the very beginning. Not the beginning of voids themselves, but the beginning of everything. The Big Bang, 13.8 billion years ago. In the first fraction of a second after the Big Bang, the universe was smaller than an atom. It contained all the energy and matter that would eventually form every star, every galaxy, every planet. Everything was compressed into a space so tiny that quantum mechanics ruled absolutely. Quantum mechanics is weird. At quantum scales, nothing stays perfectly still. Nothing remains perfectly uniform. The laws of quantum physics demand uncertainty, fluctuation, randomness. These fluctuations are incredibly tiny. They occur at scales billions of times smaller than an atom. However, they exist. They must exist. The mathematics of quantum field theory requires them. These quantum fluctuations created tiny variations in the density of energy in the early universe. Some regions had slightly more energy, some had slightly less. The differences were incredibly small. We're talking about variations of 1 part in 100,000. Then the universe inflated. In the first fraction of a second, space itself expanded exponentially. In less time than it takes light to cross the diameter of a proton, the universe grew from subatomic size to roughly the size of a grapefruit. This period is called cosmic inflation. Inflation had a profound effect on those tiny quantum fluctuations. It stretched them. It amplified them. Fluctuations that started at quantum scales got blown up to macroscopic scales, then to astronomical scales, then to cosmic scales. By the time inflation ended, these quantum whispers had become cosmic shouts. Regions with slightly higher density were now millions of light years across. Regions with slightly lower density were equally massive. However, the variations remained small, about 1 part in 100,000 still. That was enough. Gravity then took over. Over the next hundreds of millions of years, regions with slightly higher density attracted matter from their surroundings. This made them denser still, which increased their gravitational pull, which attracted more matter. A positive feedback loop. Meanwhile, regions with slightly lower density lost matter to their denser neighbors. This made them even less dense, which weakened their gravity, which made it easier for surrounding dense regions to pull away remaining matter. Another feedback loop, but running in reverse. The rich got richer, the poor got poorer. Over hundreds of millions of years and billions of years, these tiny initial fluctuations grew into the cosmic web we see today. The overdense regions became clusters and filaments. The underdense regions became voids. Computer simulations can track this process in detail. Start with a nearly uniform distribution of dark matter and normal matter. Add the tiny fluctuations derived from quantum mechanics. Let gravity operate according to Einstein's equations and watch what happens. The simulation produces walls, filaments, clusters, and voids. The results match observations remarkably well. The voids formed first. This might seem counterintuitive. You might think dense structures would form first. However, remember that voids are defined by the absence of dense structures. As soon as matter started flowing out of underdense regions into overdense regions, voids began forming. Early voids were smaller. Over time, they merged. Two neighboring voids might have a thin wall of galaxies between them. That wall contained matter, but it was spread thin. Eventually, matter in the wall got pulled away by denser regions beyond the voids. The wall thinned and vanished. The two voids merged into one larger void. This process continues today. Voids are still growing. They're still merging. The cosmic web is still evolving. The structure we observe is not final. It's a snapshot of an ongoing process that started with quantum whispers 13.8 billion years ago. Those whispers have become the defining features of the universe, and they will shape the cosmos's future for trillions of years to come. However, the story of void formation has another twist. Gravity's amplification. Imagine the universe 300 million years after the Big Bang. No stars exist yet. No galaxies. Just gas, hydrogen, and helium spread through space in a nearly uniform fog. Nearly, but not quite. In some regions, the gas is slightly denser, maybe 1 part in 10,000 denser than average. This tiny excess creates slightly stronger gravity. That gravity pulls on nearby gas, drawing it inward. As more gas accumulates, the gravity strengthens. The process accelerates. In other regions, the gas is slightly less dense, maybe 1 part in 10,000 less than average. This tiny deficit creates slightly weaker gravity. Nearby dense regions pull gas away. As gas leaves, the gravity weakens further. The process accelerates in reverse. This is a fundamental mechanism driving cosmic structure formation. Gravity amplifies initial small differences into enormous contrasts. The first dense regions to collapse were small. They contained enough matter to form a star or a small cluster of stars. These first stars appeared around 100 million years after the Big Bang. They were massive, hot, and short-lived. They burned through their fuel in just a few million years, then exploded. However, the collapse didn't stop there. The gravitational attraction continued, pulling in more matter. Small structures merged to form larger structures. Dozens of small clumps combined to form protogalaxies. Protogalaxies merged to form galaxies. Galaxies clustered together under mutual gravity. This hierarchical growth continued for billions of years. It continues today. Small structures merge to form larger structures. Galaxies join groups. Groups join clusters. Clusters align into filaments. Filaments outline voids. Meanwhile, the underdense regions got emptier. Any matter remaining in these regions felt gravitational pulls from all directions. Dense regions surrounded the voids like a shell. Matter flowed outward toward that shell, leaving the interior even more empty. By about 1 billion years after the Big Bang, the basic structure of the cosmic web had formed. Voids existed. Filaments existed. Clusters were forming. However, everything was smaller, less pronounced than today. The voids were smaller, the filaments were thinner. The clusters contained fewer galaxies. The universe has spent the last 12.8 billion years amplifying these structures. The rich regions got richer, clusters grew more massive, filaments grew more defined. The poor regions got poorer, voids grew larger and emptier. This process has a name: gravitational instability. Any small perturbation in density grows exponentially over time if gravity is the dominant force. The growth rate depends on the initial perturbation size, the amount of matter involved, and how fast the universe expands. In the early universe, expansion was faster. This limited how quickly structures could grow. Gravity had to fight against the rapid expansion. As the universe aged and expansion slowed, structure formation accelerated. Voids could grow faster. Clusters could pack more tightly. Today, we observe the result of this 13.8 billion year process. The universe is dramatically lumpy. However, it's still evolving. If we could watch the universe and fast forward, we would see the voids continuing to grow. We would see filaments slowly dissolving as voids pushed against them. We would see clusters becoming more isolated as the space between them grew. The rich getting richer and the poor getting poorer is not just an economic metaphor. It's a fundamental principle of gravitational dynamics. It explains how tiny quantum fluctuations became the largest structures in the universe. However, one mystery remains. The Boötes Void is too large. According to calculations, a void this size should not have had enough time to form since the Big Bang. The universe is only 13.8 billion years old. Simulations suggest forming a void this massive requires longer. This timeline problem troubles cosmologists. Either something special happened in the region that became the Boötes Void, or our understanding of structure formation is incomplete. The bubble merger. One proposed solution involves void mergers. Take a bowl. Fill it with soapy water. Blow bubbles. Watch what happens when bubbles touch. They merge. Two small bubbles become one larger bubble. Three bubbles might merge into one even larger bubble. The soap film between them ruptures. The air inside combines. A new, bigger bubble emerges. The same process might explain the Boötes Void. Instead of forming as a single, enormous void from the beginning, it may have started as multiple smaller voids. Over billions of years, these smaller voids expanded until their edges met. The thin walls of galaxies between them got pulled away by denser regions outside the void complex. The walls dissolved. The voids merged. This theory explains how a void as large as the Boötes Void could form in the time available since the Big Bang. Small voids can form relatively quickly. Merging them into supervoids takes longer, but the timeline works out better than trying to form a supervoid directly. Evidence supports this bubble merger model. Astronomers have found that the 60 galaxies inside the Boötes Void don't scatter randomly. Many of them align in a tube-like structure running through the void's interior. This tube might mark the boundary where two or more smaller voids met. The galaxies there represent the remnants of the wall that once separated the smaller voids. Picture two soap bubbles side by side, touching. Where they meet, you see a flat film of soap between them. Now imagine that film slowly thinning and eventually vanishing as the bubbles merge. Any tiny particles floating in the soap film would end up roughly along a line where the film used to be. The void galaxies behave similarly. The bubble merger process happens throughout the universe. Astronomers have identified many examples of small voids merging into larger ones. They've observed thin sheets of galaxies dissolving as voids on either side push outward. The cosmic web is dynamic, constantly rearranging itself. However, the bubble analogy breaks down in important ways. Soap bubbles exist in three-dimensional space. They're two-dimensional surfaces enclosing volumes of air. The cosmic web exists in three-dimensional space too, but its structures are fully three-dimensional. Voids are spherical or irregular three-dimensional regions, not surface bubbles. Also, soap bubbles merge because of surface tension in the soap film. Cosmic voids merge because matter gets pulled away from the walls between them by gravity. The driving forces are completely different. Still, the visual analogy helps. When you look at a computer simulation of cosmic structure formation, the resemblance to soap foam is striking. The universe looks like foam. Dense matter outlines bubble-shaped voids. Where bubbles meet, you get sheets and filaments. Where multiple bubbles meet, you get clusters. The foam-like structure is not unique to our universe. Any universe governed by gravity and starting with small, random fluctuations would develop similar structure. It's a natural consequence of how gravity organizes matter. The Boötes Void likely formed from the merger of several smaller voids, each perhaps 50 to 100 million light-years across initially. As these voids expanded over billions of years, they encountered each other. The walls between them contained galaxies, but those walls were already thin compared to the dense regions outside the void complex. Gravity from the surrounding dense regions pulled matter out of these walls. The galaxies in the walls were attracted to the rich clusters and filaments beyond the voids. Slowly the walls thinned. Eventually they largely disappeared, leaving only a sparse trail of galaxies marking where they once existed. This process took billions of years. It's still happening. The Boötes Void is still growing. The remaining galaxies inside it are still being pulled toward its edges. In another few billion years, even fewer galaxies will remain in the interior. The bubble merger model has become the leading explanation for how supervoids form. However, it's not the only factor. Something else happens in voids that makes them grow faster than merger alone can explain. That something is the subject of intense research. The 60 galaxies. 60 galaxies. That's all that remains in the Boötes Void. 60 islands of light scattered across 330 million light-years of near-nothingness. Each one is isolated, alone, separated from its neighbors by tens of millions of light years. These void galaxies are strange. They evolved in the most extreme isolation possible. No neighbors pulled on them gravitationally. No collisions stripped away their gas. No dense cluster environment harassed them with hot plasma. They spent billions of years in cosmic solitude. This isolation shaped them. Most void galaxies are small. Astronomers classify them as dwarf galaxies, containing only a few billion stars instead of the hundreds of billions found in large galaxies, like the Milky Way. Their small size makes sense. Large galaxies typically form through mergers, when smaller galaxies collide and combine. In voids, galaxies rarely encounter each other. Mergers don't happen. Galaxies stay small. Many void galaxies show irregular shapes. They lack the elegant spiral arms of the Milky Way or the smooth elliptical forms of cluster galaxies. Instead, they appear lumpy, patchy, disorganized. Without gravitational interactions to stir their contents and drive organized structure, they retain a more primitive appearance. Void galaxies are often rich in gas, specifically neutral hydrogen gas, the raw material for star formation. In dense environments, galaxies can lose their gas through several processes. Ram pressure stripping occurs when a galaxy moves through hot intergalactic gas in a cluster the way a car moving through water experiences resistance. The pressure pushes the galaxy's gas out. Void galaxies don't experience this. They retain their gas. Some void galaxies have surprisingly high rates of star formation given their small size and isolation. They slowly convert their abundant gas into new stars. The process happens at a leisurely pace, without the dramatic bursts of star formation that occur when galaxies collide. These galaxies will continue forming stars for many billions of years. Astronomers have observed that void galaxies tend to be blue in color. Blue light comes from young, hot, massive stars. The blue color indicates ongoing star formation. In contrast, galaxies in dense clusters often appear red, dominated by older stars. Their star formation was quenched long ago when their gas got stripped away. The 60 galaxies in the Boötes Void are hard to observe. They're faint. Most shine at magnitude 15 or dimmer, which is about 10,000 times fainter than the faintest stars visible to the naked eye. Even large amateur telescopes can barely detect the brightest few. The brightest void galaxy, designated Markarian 848, appears as a tiny, elongated smudge. It measures about 1 arcminute in length, roughly 1/30th the diameter of the full moon. Its nucleus is brighter than its outer regions, making it slightly easier to spot. However, you need at least a 10-inch telescope, dark skies, and patience to see it. Other void galaxies are even fainter. Many require professional-class telescopes with large light-collecting mirrors and sensitive cameras. Studying these galaxies in detail requires extended observations at major observatories. Despite their isolation, void galaxies provide valuable scientific information. They represent a control group for studying galaxy evolution. How do galaxies develop when left alone? What properties do they have without environmental influences? Void galaxies answer these questions. They also preserve information about the early universe. Without major mergers scrambling their structure, void galaxies retain clues about their formation. They're more pristine, less evolved, more representative of what galaxies looked like billions of years ago. Studying void galaxies is challenging but rewarding. They force us to confront what happens in the most extreme isolation the universe offers. They show us that even in near absolute emptiness, matter can organize itself into structures capable of forming stars and potentially planets. The void is empty, but it's not completely empty. Ghosts in the machine. However, emptiness is not the only thing filling voids. Neutrinos are ghosts. They're subatomic particles with almost no mass and virtually no interaction with ordinary matter. Billions of neutrinos pass through your body every second. You never feel them. They slip through atoms like light through glass, barely noticing matter exists. These ghost particles travel freely through the universe. They stream across cosmic distances, passing through gas clouds, stars, planets, and even black holes with barely any deflection. Nothing stops them. Nothing slows them. Cosmic voids are neutrino highways. In dense regions like galaxies and clusters, neutrinos still pass through, mostly unaffected. However, the gravitational fields in these regions can slightly deflect neutrino paths. The effects are tiny but measurable over cosmic distances. In voids, even these tiny effects diminish. The gravitational fields are so weak that neutrinos travel in nearly perfect straight lines. This makes voids incredibly valuable for neutrino astronomy. Scientists can study neutrinos passing through voids and compare them to neutrinos passing through dense regions. The differences reveal information about both neutrino properties and the structure they traverse. Neutrinos come in three types called flavors: electron neutrinos, muon neutrinos, tau neutrinos. These particles can transform from one flavor to another as they travel. This transformation is called neutrino oscillation. The rate of oscillation depends on the neutrino's mass. We know neutrinos have mass. However, we don't know exactly how much. Measurements suggest the masses are incredibly tiny, less than a millionth the mass of an electron. However, even these tiny masses matter when multiplied across the entire universe. The total mass of all neutrinos in the cosmos might rival the total mass of all visible stars. Voids provide ideal laboratories for measuring neutrino properties. The free-streaming neutrinos crossing voids carry information from distant sources, undisturbed by matter. Future experiments hope to use voids as natural neutrino detectors, analyzing how neutrinos behave when traveling through nearly perfect emptiness. The relationship between neutrinos and voids works both ways. Neutrinos affect void evolution. In the early universe, neutrinos streamed freely from dense regions into underdense regions. This streaming carried energy and momentum, influencing how voids formed and grew. Computer simulations that include neutrino free streaming predict slightly different void properties than simulations that ignore neutrinos. These differences are subtle. However, by carefully measuring void sizes, shapes, and distributions, astronomers can constrain neutrino properties. This is called using voids as cosmological probes. The voids themselves become scientific instruments. Several upcoming missions plan to exploit this. The Euclid satellite, launched in 2023, is mapping the distribution of galaxies across the universe. This mapping includes identifying and characterizing voids. By comparing observed void properties to simulations with different neutrino masses, scientists hope to determine the sum of all three neutrino mass values. Other experiments look at neutrinos more directly. Neutrino observatories like IceCube, buried in Antarctic ice, detect occasional neutrinos from distant cosmic sources. By studying which neutrinos pass through voids versus which pass through dense regions, researchers can test theories about neutrino behavior. The neutrinos themselves don't care about voids. They barely notice the difference between empty space and solid matter. However, that's precisely what makes them useful. They're unbiased probes. They report on conditions throughout the universe without getting tangled up in local details. In a sense, neutrinos reveal the void's true nature. From a neutrino's perspective, a void and a galaxy cluster are both nearly transparent. The void is just slightly more transparent. This perspective highlights how empty even dense regions are. From a particle physics viewpoint, atoms are mostly empty space. Galaxies are mostly empty space. The universe is mostly empty space. Neutrinos experience the universe as almost entirely void, with occasional, rare interactions scattered across cosmic distances. They're the perfect particles for studying the perfect emptiness of cosmic voids, the magnetic ghost. But there's something else in voids that's harder to detect. Space is not empty. Even in the deepest voids, invisible fields thread through the darkness. Magnetic fields, incredibly weak, but definitely present. In 2015, scientists made a startling discovery. They were studying blazars, which are supermassive black holes in distant galaxies that shoot jets of high-energy particles toward Earth. These jets emit gamma rays, the highest energy form of light. As gamma rays traveled billions of light years through space, crossing cosmic voids, something happened. The gamma rays didn't arrive exactly as expected. They showed signs of deflection, as if something had slightly bent their paths. That something was magnetic fields in the voids. The strength of these fields is almost incomprehensibly small, about 1017 Gauss. For comparison, Earth's magnetic field is about half a Gauss. A refrigerator magnet produces about 100 Gauss. The void's magnetic field is 100 million trillion times weaker than a fridge magnet. Yet, this ghost of a magnetic field is real and measurable. It affects the highest energy particles crossing cosmic distances. The deflection is tiny but detectable with careful analysis. Where do these magnetic fields come from? This question puzzles scientists. Several theories exist. One possibility is primordial magnetogenesis. This complicated term means magnetic fields might have formed in the very early universe, within the first second after the Big Bang. Quantum processes in the extreme conditions of the nascent cosmos could have created seed magnetic fields. These seeds would then get stretched and diluted as the universe expanded, producing the weak fields we detect today. Another possibility is that magnetic fields formed later, produced by the first stars and galaxies. These objects generate magnetic fields through dynamo processes, where moving electrically charged plasma creates magnetic fields. Once created, these fields could spread into the surrounding space, eventually reaching even the voids. A third possibility involves cosmic rays. These high-energy particles streaming through space carry electrical charge. Moving charges create magnetic fields. Perhaps cosmic rays traversing voids generate weak magnetic fields as a side effect. The truth might involve all three processes. Primordial fields provide a seed. Galactic fields add structure. Cosmic rays maintain and reinforce the fields. The result is a weak but pervasive magnetic skeleton threading through the cosmic web, including the voids. These magnetic fields have consequences. They affect how charged particles move through space. They influence the formation of structure. They might even play a role in galaxy formation by providing pressure support against gravitational collapse. Studying void magnetic fields is difficult. The fields are so weak that only indirect detection methods work. Scientists rely on analyzing how high-energy particles get deflected during their journey across the universe. This requires detailed observations of distant sources combined with sophisticated modeling. Future telescopes and instruments will improve our ability to map these magnetic ghosts. Understanding the magnetic structure of voids will reveal information about the early universe, about how magnetic fields formed and evolved, about the complex interplay between matter, energy, and fields in the voids contain magnetic fields. They also contain photons, the particles of light constantly streaming through in all directions. They contain cosmic rays, high-energy particles ejected from exploding stars and supermassive black holes. They contain gravitational waves ripples in space-time itself, passing through unimpeded. The voids are not empty. They're just empty of ordinary matter. The stuff we're made of, the stuff stars are made of, barely exists in voids. However, other forms of matter and energy fill them. And there might be something else lurking in the voids, something even harder to detect. The cold spot. In 2003, scientists studying the cosmic microwave background radiation discovered something odd. The cosmic microwave background, often abbreviated CMB, is the afterglow of the Big Bang. It's light that's been traveling through space for 13.8 billion years, stretched by the universe's expansion into microwave wavelengths. The CMB is remarkably uniform in every direction. It is almost exactly the same temperature, about 2.7 degrees above absolute zero. However, almost exactly hides tiny variations. Some patches are slightly warmer, some slightly cooler. These temperature differences are about 1 part in 100,000. These tiny variations are incredibly important. They represent the seeds of all cosmic structure. Warmer spots correspond to regions that were slightly denser in the early universe. Cooler spots correspond to less dense regions. The pattern of warm and cool patches encodes information about the universe's composition, age, and evolution. However, one spot in the CMB is too cold, much colder than it should be. The WMAP satellite, which mapped the CMB in exquisite detail, found this cold spot in the constellation Eridanus. It's about 10 degrees across on the sky, roughly 20 times the moon's apparent diameter. The temperature in this spot is about 70 microkelvins colder than the surrounding average. That might not sound like much. However, according to standard cosmological models, a spot this large and this cold is improbable. Not impossible, but unlikely. The chance of such a feature appearing randomly is less than 1%. Scientists have proposed various explanations. Some suggest it's just a statistical fluke. With billions of spots across the sky, one unusually cold one isn't shocking. Others propose more exotic explanations involving collisions with other universes or tunneling effects from other dimensions. However, one explanation stands out as most plausible: a supervoid. The cold spot might be caused by an enormous void between us and the CMB. This void would be truly massive, perhaps 120 megaparsecs across. That's about 400 million light-years bigger than the Boötes Void. Here's how it works. Light traveling through a void experiences something called the integrated Sachs-Wolf effect. When light enters a void, the void's weak gravity slightly blue shifts it, giving it a tiny bit more energy. When the light exits the void, the gravity slightly red shifts it, removing energy. Normally, these effects cancel perfectly. However, if the universe is accelerating its expansion, which it is, the void grows while light travels through it. The void is deeper and larger when the light exits than when it entered. The red shift on exit is slightly stronger than the blue shift on entry. The light loses a tiny amount of energy overall. This energy loss makes the light appear colder. If a truly enormous void sits between us and a particular patch of the CMB, the light from that patch would lose more energy than light from other directions. We would observe it as a cold spot. Computer simulations show that a supervoid of the right size in the right location could create a cold spot matching observations. The void would need to be extraordinarily large and positioned at a specific distance from Earth. However, such voids are rare but possible in the standard cosmological model. Surveys have searched for evidence of this hypothetical supervoid. They found weak evidence for a depression in galaxy density along the line of sight to the cold spot. However, the evidence is not conclusive. More observations are needed. If the cold spot is caused by a supervoid, it would be the largest void ever detected. It would also confirm that the integrated Sachs-Wolf effect operates as predicted, providing independent evidence for dark energy driving accelerated expansion. However, if the cold spot is not caused by a supervoid, explanations become more exotic and controversial. It might indicate something wrong with our understanding of the universe's large-scale structure or evolution. The cold spot remains one of the most intriguing mysteries in cosmology. It's a single anomalous feature in otherwise excellent agreement between observations and theory. It might be nothing. It might be everything. And it might be a void's signature, the vacuum energy. Which raises a question. If voids can affect the light from the cosmic microwave background, what else can they affect? Here's a paradox. Take everything out of a region of space. Remove all the atoms. Remove all the particles. Remove all the radiation. What remains? Nothing. Wrong. Remove all matter and energy from a volume of space, and you're left with a vacuum. However, the vacuum is not nothing. The vacuum is something. It's space itself. And space has properties. It has energy. It vibrates with quantum fields. This sounds like word games. It's not. The vacuum of space has measurable physical effects. The most famous is the Casimir effect, first measured in 1948. Place two metal plates very close together in a vacuum. They attract each other with a tiny force. This force comes from the vacuum itself. Quantum fields between the plates behave differently than quantum fields outside the plates, creating a pressure imbalance. The plates feel this pressure and move together. The vacuum is full of quantum fields. There's an electron field, a quark field, a photon fields for every type of particle. These fields exist everywhere, always. They're not matter. They're more fundamental than matter. Particles are just excitations in these fields' ripples on an underlying ocean. Even when no particles are present, the fields remain. They vibrate with zero-point energy, the minimum energy allowed by quantum mechanics. You can't remove this energy. It's built into the structure of space. Cosmic voids are nearly empty of matter. However, they're completely full of quantum fields. Every cubic centimeter of void space contains the vacuum energy of all quantum fields. This energy is small, incredibly small. However, it's not zero. Scientists call this vacuum energy dark energy. It's the mysterious component driving the accelerated expansion of the universe. Dark energy appears to make up roughly 68% of the universe's total energy content. It's the dominant form of energy in the cosmos. In dense regions like galaxies and clusters, dark energy is overwhelmed by other forces. Gravity from ordinary matter is much stronger locally. Dark energy has no noticeable effect. You could remove dark energy entirely, and Earth's orbit around the Sun would not change. Stars would burn the same, galaxies would hold together. However, in voids, dark energy dominates. There's almost no ordinary matter to compete with the weak vacuum energy. It becomes the strongest force. And what does dark energy do? It pushes space apart. It causes expansion. Voids expand faster than the cosmic average because dark energy dominates there. The void regions contain matter densities 1/10 the cosmic average or less. Dark energy, meanwhile, has the same density everywhere. It doesn't dilute as space expands. More space means more dark energy. This creates a feedback loop. Voids expand because they contain mostly dark energy. Expanding voids become even emptier. Even emptier voids let dark energy dominate more completely. The expansion accelerates. This process is actively reshaping the universe. Voids are growing. They're pushing on the surrounding walls and filaments. They're driving galaxies apart despite gravitational attraction. Over billions of years, voids will dissolve the cosmic web. So the voids are not empty. They're full of vacuum energy, full of quantum fields, full of the very fabric of space-time itself, vibrating with zero-point fluctuations. This realization changes how we think about voids. They're not passive absences. They're active participants in cosmic evolution. They're the places where dark energy does its work. They're the engines driving the universe's accelerated expansion. Understanding voids means understanding dark energy. Understanding dark energy means understanding the universe's fate. Will expansion continue forever? Will it accelerate without limit? Will distant galaxies eventually recede faster than light, disappearing beyond our cosmic horizon? The answers lie in the voids, in the nothing that's actually something. The dark energy enigma. Physicists discovered dark energy by accident. In the late 1990s, two teams studying distant supernova explosions expected to measure how much the universe's expansion was slowing down. Gravity should pull everything together, decelerating the expansion left over from the Big Bang. Instead, they found acceleration. The universe wasn't slowing down, it was speeding up. Galaxies were flying apart faster today than they were billions of years ago. Something was pushing space itself to expand at an increasing rate. They had no idea what caused this. They still don't. So they gave it a placeholder name, dark energy. The name means we don't know what this is. It's an admission of ignorance dressed up in scientific terminology. Dark energy has strange properties. Unlike matter, which dilutes as space expands, dark energy maintains constant density. Create more space and you get more dark energy. It's a property of space itself, not something moving through space. Dark energy also has negative pressure. This sounds abstract, but it has real consequences. Negative pressure creates repulsive gravity. Instead of pulling things together, it pushes them apart. The more space you have, the more dark energy you have, the stronger the push becomes. However, this pushing only matters where there's enough space without much matter to counteract it. On Earth, dark energy is completely irrelevant. The planet's gravity dominates. The electromagnetic forces holding atoms together dominate. Dark energy's effect is so tiny that it rounds to zero. You could turn off dark energy entirely, and nothing on Earth would change. The same applies throughout the solar system. Planetary orbits wouldn't shift. The distance between planets wouldn't grow. Gravity wins easily. Even in interstellar space within the Milky Way, dark energy barely matters. The galaxy's gravity holds everything together. Stars orbit the galactic center. Gas clouds collapse to form new stars. Dark energy's push is negligible. In galaxy clusters, dark energy still loses. These clusters contain hundreds or thousands of galaxies bound by mutual gravity. The gravitational attraction is strong enough to overcome dark energy's expansion. Clusters hold together. Where does dark energy win? Voids. In voids, there's almost no matter. Gravity is incredibly weak. Nothing holds space together. Dark energy's push, tiny as it is, becomes the dominant force. For the first time, it can actually do something. Voids are dark energy's playground. They're the only environments in the universe where dark energy can stretch space without fighting against overwhelming gravity. The result: voids expand faster than anywhere else. Measurements confirm this. Observations show that void regions grow at rates exceeding the cosmic average expansion. The difference is small but measurable. A void today is larger than simple universal expansion would predict. This accelerated void expansion has profound implications. It means dark energy is actively reshaping the universe's structure. The voids push outward on the filaments and walls surrounding them. This pushing drives galaxies apart, even within filaments, where gravity should hold them together. Think of the cosmic web as a sponge being stretched. The holes in the sponge get larger. The solid material gets thinner, spreading across more space. Eventually, the sponge becomes so stretched that the solid parts break apart into disconnected pieces. That's what dark energy is doing through the voids. Computer simulations that include dark energy show the cosmic web slowly dissolving. Filaments thin, walls fragment. Clusters become isolated. The voids win. Without voids, dark energy would still exist. However, it would struggle to affect the universe's structure. With voids, dark energy has space to work. It has room to push. It has the opportunity to reshape everything. Scientists studying dark energy focus increasingly on voids. The voids are where the action happens. They're the laboratories where dark energy's effects appear most clearly. They're the key to understanding what might be the universe's most mysterious component. Dark energy defines the universe's future, and that future is being written in the voids, the time dilation. But wait, what if the relationship between voids and dark energy is even stranger? Einstein taught us that time is not absolute. It flows at different rates depending on gravity. Strong gravity slows time. Weak gravity lets time flow faster. This effect is real and measurable. Atomic clocks on satellites tick slightly faster than identical clocks on Earth's surface. The difference is tiny, just microseconds per day, but GPS satellites must account for it, or navigation would fail. Now, imagine the most extreme case. Place one clock inside a galaxy, surrounded by billions of stars and massive dark matter. Place another identical clock in the deepest part of a cosmic void, hundreds of millions of light years from the nearest galaxy. The void clock ticks faster, much faster. According to calculations, a clock in the Milky Way runs about 35% slower than a clock in an average cosmic void. This means that for every 100 years that pass in our galaxy, 135 years pass in the void. Over cosmic timescales, this difference becomes enormous. Since the Big Bang, about 13.8 billion years have passed as measured by clocks in galaxies like ours. However, measured by clocks in the deepest voids, billions more years have elapsed. The voids are older, not in the sense that they formed earlier, but in the sense that more time has passed there. This time difference affects everything. Space expands. In 100 years of galaxy time, space in a galaxy expands by a certain amount. However, in the void, 135 years pass. Space has more time to expand. It expands more from the galaxy's perspective. The void appears to be expanding faster. However, from the void's perspective, nothing unusual is happening. It's just that more time has passed, so more expansion has occurred. This insight comes from a theory called timescape cosmology. It suggests that the universe's apparent acceleration might not be real acceleration at all. It might be an illusion caused by not properly accounting for how time flows differently in different environments. Imagine two runners on a track. One runner is in normal gravity. The other runner experiences weaker gravity where time flows faster. Both runners move at the same speed relative to their local time. However, the runner in weaker gravity experiences more time, so covers more distance. From an external observer's perspective, that runner appears to be accelerating. The universe might work similarly. Voids don't actually expand faster in their local time. They just have more local time available. The acceleration we observe might be a bookkeeping error, a failure to account for time dilation properly. If true, this would eliminate the need for dark energy. The mysterious force pushing the universe apart might not exist. The acceleration would be explained by the lumpy structure of space and its effect on time. The timescape model remains controversial. Most cosmologists still favor dark energy as the explanation for cosmic acceleration. However, recent high-precision measurements have revived interest in alternative explanations. The model makes specific predictions. Voids should have certain size distributions. The cosmic microwave background should show particular patterns. Galaxy clustering should follow certain rules. Observations are beginning to test these predictions. Early results are intriguing. Some data fit the timescape model better than standard dark energy models. The differences are subtle, but they're there. More observations are needed to determine which model better describes reality. What's certain is that time behaves strangely in voids. Whether this explains dark energy or simply adds another layer of complexity to void physics, it matters. Time is not the same everywhere. The universe does not tick uniformly. Clocks in voids race ahead of clocks in galaxies. The universe ages unevenly. Some regions are older than others, not because they formed earlier, but because time flows faster there. A radical alternative. This raises a profound question. If dark energy might be explained by differential time flow, what else about our cosmological understanding might be wrong? For over 25 years, cosmologists have assumed dark energy exists. They've built theories around it. They've designed experiments to measure its properties. They've accepted it as a fundamental component of the universe. What if they're wrong? The timescape model offers a radical alternative. It says the universe's structure itself creates the illusion of acceleration without needing any mysterious dark energy. The key is understanding how lumpy structure affects observations. Standard cosmology uses equations developed a century ago. These equations assume the universe is smooth and uniform at large scales. They treat the cosmos like a perfectly mixed soup, expanding uniformly in all directions. This assumption is called the Friedmann-Lemaitre model. However, the universe is not smooth. We know this. The cosmic web exists. Voids and filaments dominate the structure. The Friedmann equations are approximations that work well for average properties, but might fail to capture important details. The timescape model abandons the smoothness assumption. It treats the universe as fundamentally lumpy. Different regions expand at different rates. Time flows at different speeds. Observations from one region don't straightforwardly translate to understanding other regions. Here's the key insight. When we measure distances to distant galaxies, we're looking through a complex landscape of voids and filaments. Light travels through regions with different expansion rates and time flows. We need to account for all this complexity. If we use simple smooth universe equations, we might misinterpret what we see. We might conclude that expansion is accelerating when actually we're just not properly accounting for the lumpy structure. The timescape model makes specific mathematical predictions. It calculates how light propagates through the cosmic web. It accounts for time dilation in voids versus filaments. It produces predictions for how distant supernova should appear. In 2024, researchers tested the timescape model using the Pantheon Plus dataset. This dataset contains observations of 1,500 type A supernova, the largest and most precise collection ever assembled. These supernovas serve as standard candles for measuring cosmic distances. The analysis compared two models. First, the standard lambda cold, dark matter model with dark energy. Second, the timescape model without dark energy. Which one fit the data better? The result shocked many cosmologists. The timescape model fit the supernova data slightly better than the standard model. The difference was small, but statistically significant. The data actually preferred the model without dark energy. This doesn't prove the timescape model is correct. Science rarely works through single definitive proofs. However, it demonstrates that alternatives to dark energy deserve serious consideration. The assumption that dark energy exists might be premature. Additional evidence comes from other cosmological tensions. The Hubble tension, for example. Different methods for measuring the universe's expansion rate give different answers. They disagree by about 10%. This disagreement has persisted for years despite increasingly precise measurements. The timescape model might resolve this tension. If we're not properly accounting for local structure, our local measurements might be biased. Correcting for timescape effects could bring different measurements into agreement. The cosmic microwave background also shows anomalies. The data doesn't perfectly match predictions from the standard model. The timescape model might explain some of these anomalies differently. Critics point out challenges. The timescape model requires complex calculations. It's harder to work with than the smooth universe equations. Also, it needs to explain all cosmological observations, not just supernova. Tests are ongoing. Future telescopes will gather more data. The Euclid satellite is mapping galaxy distributions. The Nancy Grace Romang Space Telescope will observe thousands more supernovae. These observations will test both models more rigorously. Within a decade, we might know whether dark energy exists or whether it's an illusion created by cosmic structure. The voids hold the answer. There, where the differences between models appear most clearly. If the timescape model wins, textbooks will need rewriting. Our understanding of the universe's composition and fate will change dramatically. 68% of the universe currently attributed to dark energy might not exist. The voids might be even more important than we thought. The local void. In 2013, 3 astronomers made an uncomfortable discovery. They were analyzing galaxy distributions in our cosmic neighborhood, mapping structures within a few billion light years of Earth. The pattern they found was disturbing. We appear to live inside a void. Not a complete void like Boötes, but a significant underdensity. The region surrounding our galaxy contains 10 to 20% fewer galaxies than the cosmic average. This depression extends roughly 2 billion light years across. Scientists call it the KBC void, named after the 3 astronomers who identified it: Keenan, Barger, and Cowie. Some call it the local hole. Either way, it's an uncomfortable realization. We're not in a typical environment. We're in a cosmic desert. The KBC void is not as empty as Boötes. It contains many more galaxies. The density is only moderately reduced, not 97% depleted. However, it's real, and it affects our observations of the universe. Living inside a void creates biases. When we measure the expansion rate of the universe, we're measuring from inside an underdense region. Galaxies inside voids experience an extra gravitational pull outward from the denser regions surrounding the void. This extra pull could make the expansion appear faster locally than it actually is on average. This might explain the Hubble tension. Local measurements of cosmic expansion give one number. Measurements from the distant cosmic microwave background give a different number. The discrepancy is about 10%, matching roughly the density deficit of the KBC void. If we're in a void, our local measurements are biased. They don't represent the cosmic average. Correcting for this bias might resolve the tension. However, here's the problem. Not everyone agrees the KBC void exists. Galaxy surveys are incomplete. We can't see every galaxy. Faint galaxies escape detection. Dust clouds in our own galaxy block views in some directions. Determining whether our local region is truly underdense or just appears underdense due to observational limitations is challenging. Some studies confirm the void's existence. They find clear evidence of reduced galaxy density in our neighborhood. Other studies question it. They suggest the apparent underdensity might be a statistical fluke or an artifact of how galaxies are counted. In 2025, a team used computer simulations to test whether the KBC void could exist. They fed galaxy survey data into simulations and let the computer reconstruct the full three-dimensional distribution of matter, filling in gaps where observations are incomplete. Their results cast doubt on the void. The simulations suggested our region might be closer to average density than previously thought. However, the debate continues. If the KBC void exists, it has profound implications. It means our view of the universe is skewed. Our position in cosmic structure affects what we see and how we interpret observations. Cosmology is hard enough without positional biases. It also means the Boötes Void might not be as exceptional as we thought. If we live in a moderately underdense region 2 billion light-years across, and the Boötes Void is a severely underdense region 330 million light-years across, perhaps large voids are more common than surveys suggest. We might see fewer voids simply because we're inside one. From inside a void, detecting other distant voids becomes harder. They blend into the background. Only the most extreme ones, like boats, stand out clearly. The possibility that we occupy a special location in cosmic structure is philosophically uncomfortable. The Copernican principle suggests we should not be in a special place. Earth is not the center of the solar system. Our galaxy is not the center of the universe. We occupy a typical, unremarkable position. Or do we? If we're inside a void, we're in a minority environment. Most galaxies live in average or overdense regions. We're in the 20% of space that's underdense. That's not typical. That's somewhat unusual. Living in a void might also explain why life developed on Earth. Voids are quieter, fewer supernovae nearby, less cosmic radiation bombardment. Perhaps void locations are safer for complex life to evolve. Or perhaps we're overthinking it. Perhaps the KBC void doesn't exist, and this is all speculation based on incomplete data. Either way, the question matters. Where we are affects what we see. The thought experiment. Astronomer Greg Aldering once calculated something haunting. He asked what the universe would look like if the Milky Way had formed at the center of the Boötes Void instead of its actual location. His answer: we wouldn't have known other galaxies existed until the 1960s. Think about that. For all of human history, every civilization that ever studied the night sky would have seen only the Milky Way. Ancient astronomers would map stars. They would identify planets. They would discover that stars form patterns that repeat. However, they would never see another galaxy. The telescope would arrive in the 1600s. Astronomers would peer deeper into space. They would resolve individual stars and nebulae. They would chart star clusters. However, still no other galaxies, just our own. Photography would revolutionize astronomy in the 1800s. Long exposures would reveal faint objects invisible to the eye. Astronomers would catalog millions of stars. They would discover the Milky Way's spiral structure. However, the universe would appear to contain only one galaxy, ours. In the early 1900s, the Great Debate would never happen. This was a famous dispute between astronomers about whether spiral nebulae were distant galaxies or nearby gas clouds within the Milky Way. The answer changed our understanding of cosmic scale. However, from the Boötes Void center, the answer would be obvious. No distant galaxies exist. The universe is just the Milky Way. Einstein would still develop general relativity. However, when he applied his equations to cosmology, he might conclude the universe was static and finite, containing just one galaxy. The observational evidence would support this. The expansion of the universe would remain undiscovered. Edwin Hubble's breakthrough in the 1920s depended on measuring distances to other galaxies and finding that more distant ones recede faster. No other galaxies means no discovery of expansion. The Big Bang theory might never develop. Without evidence for expansion, scientists would lack the key clue that the universe had a beginning. Cosmology would stagnate. Only in the 1960s would telescopes become powerful enough to detect the faint void galaxies at the edge of the Boötes Void, hundreds of millions of light years away. Suddenly, astronomers would discover the universe is far larger than they thought. Other galaxies exist. They're just incredibly distant. This discovery would revolutionize science nearly overnight. The universe would expand from one galaxy to potentially billions. The realization that we lived in a vast, empty region surrounded by a cosmos full of galaxies would be shocking. However, wait. The revelation gets stranger. From the Boötes Void center, astronomers would eventually map the universe. They would discover that galaxies cluster in a shell surrounding their position. They would realize they occupy the center of an enormous void. The temptation to conclude they're in a special position would be overwhelming. The Copernican principle would face a severe challenge. We're clearly not in a typical location. We're in the middle of the biggest empty region in the universe. That seems special. That seems designed. Religious and philosophical implications would explode. Scientists would struggle to explain why we happen to sit at the center of such a unique structure. Coincidence? Observer selection effects? Some deeper principle? Eventually, they might conclude that voids this large exist elsewhere. We're not at the universe's center, just at the center of one void among many. However, accepting this would require faith in theories rather than direct observation for quite some time. This thought experiment reveals how profoundly location matters. Our actual position in a typical filament gave us a relatively unbiased view of cosmic structure. We could discover other galaxies easily. We could map the cosmic web. We could develop modern cosmology. From the Boötes Void Center, cosmology would lag behind by decades or centuries. Our understanding of the universe depends not just on our technology and intelligence, but on where we happen to be. We got lucky. We live in a region where the universe is relatively transparent and informative. The dissolving web. However, the voids are not done reshaping our cosmic environment. The cosmic web is dying. Slowly, gradually, but inevitably. The voids are consuming it. Imagine a time-lapse video of the universe, sped up so that billions of years pass in minutes. You would see the voids growing, the filaments thinning, the walls fragmenting, the clusters becoming more isolated. This process is happening right now. It's been happening for billions of years. It will continue for tens of billions more. Voids expand faster than the cosmic average because dark energy dominates there. As they expand, they push on their surroundings. The walls and filaments adjacent to voids feel this push. They're being stretched, pulled apart from both sides as the voids on either side grow. Galaxies and filaments feel the effect. They're moving apart from their neighbors at rates exceeding what simple cosmic expansion would predict. The voids are actively driving them apart. This process has a name: void expansion feedback. The voids grow. Growing voids push harder. Stronger pushing accelerates void growth. The loop feeds itself. Over billions of years, filaments thin. Imagine pulling taffy. As you stretch it, it gets thinner and thinner until eventually it breaks. Filaments behave similarly. The voids pull from all sides. The filament stretches. Eventually, it can't maintain its structure. It fragments into isolated sections. Walls dissolve even faster. Their two-dimensional structures being pushed from both sides by three-dimensional voids are inherently fragile. As voids expand, walls thin to near transparency, then vanish entirely. Only clusters can resist. These dense knots of hundreds or thousands of galaxies are held together by powerful gravity. The void expansion can't break them apart. However, it can isolate them. Imagine a cluster sitting in a filament. The filament connects it to other clusters. Galaxies flow along the filament, occasionally feeding into the cluster. The cluster grows by accumulating matter from its surroundings. As voids expand, the filament thins. Fewer galaxies flow along it. The cluster's connection to the rest of the cosmic web weakens. Eventually, the filament breaks entirely. The cluster becomes an island, surrounded by expanding voids. Computer simulations project this process forward. They show that in 10 to 20 billion years, most filaments will have dissolved. Most walls will have vanished. Only clusters will remain, separated by vast, expanding voids. Each cluster will become an island universe. Galaxies within the cluster will orbit their mutual center of mass. They'll interact gravitationally. They'll merge occasionally. However, they'll have no connection to other clusters. From a galaxy inside such an island cluster, the observable universe would shrink. Distant galaxies would recede faster and faster as the voids between clusters expanded. Eventually, they would cross the cosmic horizon, receding faster than light can travel through expanding space. They would disappear from view forever. A civilization arising in such a cluster billions of years from now would observe a universe containing only their local cluster. They would see no other galaxy clusters. They would have no evidence that the universe extends beyond their island. They might develop cosmology, but their conclusions would be wrong because their observations would be incomplete. They would lack the data needed to understand the universe's true structure and history. We're lucky to live when we do. We can see the cosmic web in its middle age still structured, still connected, but beginning to show signs of dissolution. We can study both the past and the future by observing different regions at different distances. The voids are winning. They will win. The cosmic web is temporary. The voids are forever, or at least for the universe's remaining lifetime. The pressure of nothingness. However, how do voids actually push? Pressure usually requires matter. Air pressure comes from air molecules colliding with surfaces. Water pressure comes from the weight of water pushing down. We associate pressure with stuff. However, empty space has pressure too. Negative pressure. This sounds like nonsense. How can nothing exert pressure? The answer lies in Einstein's general relativity. Mass and energy don't just create gravitational attraction. They warp space-time itself. Different forms of energy warp space-time in different ways. Normal matter has positive pressure. It wants to clump together under its own gravity. Positive pressure in this context means it creates attractive gravity. More matter in one place pulls on surrounding matter. Dark energy has negative pressure. It wants to push space apart. Negative pressure creates repulsive gravity. More dark energy means stronger push. Voids are full of dark energy. They contain little normal matter, so the negative pressure of dark energy dominates. The voids literally push on space-time around them. Think of space-time as a flexible fabric, like a rubber sheet. Mass creates dips in the fabric. Bowling balls placed on a rubber sheet create wells. Smaller balls roll toward the wells. That's gravity. Dark energy does the opposite. It stretches the fabric. It creates a tension that pulls the rubber sheet tighter, pushing against anything touching it. Voids are regions where this stretching dominates. The fabric of space-time is being pulled taut from within. This creates outward pressure at the void's boundaries. Galaxies near void edges feel this pressure. It manifests as an extra push, accelerating them away from the void. The effect is small compared to the galaxy's overall motion, but it's measurable. Scientists have observed this. Galaxies adjacent to voids show peculiar velocities, extra motions beyond what cosmic expansion alone would produce. The velocities point away from void centers consistent with voids pushing outward. The pressure also affects space-time curvature. Voids create regions of slight negative curvature. Space within voids is geometrically different from space in filaments. Light paths bend differently. Distances measure differently. These curvature effects are subtle but real. They influence how we measure cosmic distances. They affect gravitational lensing. the bending of light by gravity. Careful observations can detect void effects on light from distant sources. The pressure of nothingness grows with time. As the universe ages, matter density decreases because space expands. However, dark energy density stays constant. It's a property of space itself, not something diluted by expansion. This means dark energy's relative importance increases. 10 billion years ago, matter dominated over dark energy. Voids pushed, but weakly. Today, dark energy dominates. Voids push harder. 10 billion years from now, dark energy will dominate even more. Voids will push even harder. The pressure is destroying the cosmic web, not through violence, but through patient, relentless expansion. Voids don't tear filaments apart. They stretch them until they naturally disconnect. It's a pressure that doesn't need particles. It doesn't need temperature. It needs only empty space and the quantum fields that fill it. The vacuum itself has tension. That tension creates pressure. That pressure reshapes the universe.